the interaction between light and matter. So we talked about the behavior of light, which means how that light will react when there is any media in its path, binds off such as in reflection, changing the direction such as in refraction, or even absorbed by this material. Well, that's about the light. What about the matter itself? What will happen to the matter when the light strikes it or hit it? Well, it's really important to study the interactions of light and matter because mostly it determines everything we see. It explains the colors, for example. The red flower, for example, will reflect the red, which means that flower made of material that reflects only the red light. The black absorbs all the color while the white reflects all the colors. The interaction between light and matter mostly determine the appearance of everything around us. So how does light interact with matter? Let's back to the 0 point. What is light? As we said, light is an electromagnetic waves, or sometimes it could behave like particles. We call them the photons. It's kind of energy. And it's very strange because it carries energy but without mass. So light carries energy but has no mass. And if you remember, we talked about the properties and characteristics of light. The two important quantities of waves were the wavelength with the distance between one peak to another peak or from one trough to the other trough. The wavelength or lambda. We also have the frequency, which the number of times per 1 second that wave vibrates up and down. So in this distance per 1 second, the amount of vibration determines the frequency. Wavelength and frequency inversely proportional. If the wavelength increase, the frequency will decrease and vice versa. But frequency multiplied by that wavelength will give us the velocity or the speed of the light. Velocity and the speed are the same. That when the light is wave. What about when the light is particles or what we call the photons? Each photon has a wavelength and a frequency. The energy of a photon depends on its frequency. And each photon contains energy. And to calculate the amount of energy in that photon, we have Planck constant multiplied by frequency. H is the Planck constant, which equals 6.626 times 10 to minus 34 joule in a second. So this is a constant such as the speed of light in vacuum. And as you can notice, when the frequency increases, the energy of that photon also will increase. And also that frequency will increase when the wavelength decrease. When we related those two equations to each other, we can find that also energy of the photon equal Planck's constant multiplied by the speed of the light subdivided to the wavelength. As the speed increases, the energy will increase too, and the opposite with the wavelength. The energy unit of the photon is joule. So if we solve the electromagnetic spectrum, the short wavelength immediately means a high frequency, which means the energy of photons will increase in this side of the spectrum. Quite the opposite with the long wavelength. We have low frequency, which means immediately low energy in that photons from this side of the spectrum. In our visible light, the red color contains less energy than the purple and blue color. So if you want to calculate the amount of energy in the red wavelength, we can use the previous equation to figure it out. So the equation was energy of photon equal Planck's constant multiplied by frequency. But since we don't have the frequency and we have the red wavelength, which is 700 nanometer, we can say energy of photon equal Planck's constant multiplied by the velocity or the speed of light subdivided to the wavelength. Planck's constant is 6.626 times 10 to minus 34 joule per second multiplied by the speed of light in vacuum, which is 3 times 10 to 8 meter per second, subdivided to the wavelength of the red color. And this is nanometer. We need to convert it to meter, of course. So we have to multiply it by 10 to minus 9 meter. And the result will be 2.8 times 10 to minus 19 joule. And by the way, the unit of that energy either by joule or electrovolt. And 1 joule equal 6.242 times 10 to 18 electrovolt. Let's study chemistry a little bit. We have 3 structures of matters. It could be solid, such as wood, for example. It could be liquid, such as water, or a gas, such as oxygen. All of them consist of the atom. And that atom composed of smaller nucleons surrounded by electrons. The nucleus itself turned out to be made out of even smaller particles, which is proton and neutron. And each atom of different elements has a unique structure. You will find different number of electrons in each element, different number of the positive protons, which is the atomic number, and different number of atomic mass, which is the number of protons and neutrons. Not just that, each atom has different levels. The electrons in atoms are restricted to particular energy levels or the orbits. Here in hydrogen we have just one level, while in carbon we have 1, 2 levels. Sometimes the electron needs to jump from one level to another level. Each level of those contain different amount of energy. The level near the nucleus contains the lowest amount of energy. As farther we go from the nucleus, as higher amount of energy we have. So the electron cannot just jump like that. If the electron needs to jump from low level to a higher level, that means we should give energy to that electron. And quite the opposite. If the electron in higher level, we need to take energy out of that electron to decrease its level. So that's the nucleus with protons and the neutralized neutron. And here we have the levels of energy around the nucleus. If the negative electron need to go to a higher level, we should give power or energy to that electron. So the electron will absorb that energy and jump to the higher level. So from low level to high level, that electron needs to absorb energy. What if the opposite? When that electron needs to go back again to the lower level, it should subtract that energy again to go down to the lower level. So from high to lower, the electron needs to emit energy or give energy. So emit from high to low and absorb from low to high. So the energy must be conserved. But what that has to do with the light? In the light, we have something we call it the line spectra. If we brought a source of light, such as bulb for example, and we put a prism here, the prism will separate that white light into the 7 colors, which is the dispersion of the light. If we brought a spectrometer, which is an instrument that will show us the broad beam of the light or the spectrum, the beam coming from the prism will appear like that, which is the spectrum of light. And since the colors of the wavelength are continuous without any separation, we call this kind of spectrum the continuous spectrum. And we have 3 types of spectra. Kirchhoff explained the idea of the spectra in Kirchhoff's law. He said when you put a hot, opaque body, such as the bulb for example, you will see the whole visible light without any interruption, and all the wavelengths are completely filled. And that's the continuous spectra, which a complete rainbow of color. But if we put a hot transparent gas, this will produce an emission line spectra. Which is a series of bright colors against a dark background. So that thin or low density cloud of gas emits light only at specific wavelengths that depend on its composition and temperature, producing a spectrum with bright emission lines against black background. So that type number 2, the emission spectra. Number 1 was the continuous, number 2 was the emission. The third one, in front of source of light, such as this bulb, the bulb obviously will produce a continuous spectrum. But this cloud will absorb or produce an absorption line spectrum. which is a series of dark spectral lines among the color of the continuous spectrum, which means immediately it's the opposite of emission spectrum. And if you notice, the absorption spectrum complete the emission spectrum. What are those black lines? Those black lines, the area where the photons of these wavelengths have been absorbed, so you cannot see them. If you remember when we said the black color absorb energy. So that means this emission area, there is a lot of energy. And this colorful area, when this spectra will emit energy and send it here to be absorbed by this area, so it appears as black area. So the absorption spectrum absorb energy while the emission emit or give energy. So what's the difference between emission spectra and the absorption spectra? The main differences between the emission and absorption spectra is that emission spectrum is black and has different colored lines in the spectrum. Quite the opposite in the absorption spectra, which is a continuous spectrum but with dark colored lines in the spectrum. This one produced when the atom give or release energy, and this one will produce when the atom will receive that energy or absorb energy. The emission spectra can emit all the colors in an electromagnetic spectrum, while the absorption spectrum can have a few colors missing, such as those due to the redirection of absorbed photons. So this dark area where the spectrum absorbs photons. Each matter in the universe or each element in the universe had a different spectrum from the other matter. So it's literally like the fingerprint for that matter, which means you will never find two elements have the same fingerprint. And why those kind of spectrum are helpful. For example, we find a new element in cave, and it was quite old that we cannot discover what kind of element is that. So we will read the spectrum of that element to see its fingerprint. When we have that reading, we will match it with old fingerprint to see what kind of matter is that. So let's say the reading here look like the reading of hydrogen. Immediately that old material is hydrogen. If it doesn't match anything, that's immediately a new element. We can see it also to observe the stars. So we'll see that star and the spectrum of that star to figure out what that star mostly composed of, a hydrogen, helium, just by reading its spectrum. Since different atoms of different elements have different fingerprints, that means we can stimulate them with different wavelengths. Let's say we have the atom of sodium and the mercury. Sodium and mercury. And those are their level of energy. The first, the second, the third. Same here, the first, the second, and the third. So we have the electrons here and here. Both have the yellow wavelength in their spectra. So if we strike those electrons with yellow wavelength, those electrons will absorb that energy to jump for a higher level. If those electrons emit or give away that energy, they will return back to the first level again. Emitting energy will send you back to the lower level of energy, and quite the opposite, absorption of energy will make the electron jump to the higher level of energy. But you need to strike that electron with the correct tone of color. For example, in mercury, there is a blue wavelength, but we cannot find it in the sodium. So, if you strike the electron of sodium with that blue wavelength, nothing will happen. It will remain without changing its position. What about in mercury? If you hit it with blue wavelength, it will jump to a higher level. And this time higher than the second one because blue color contain a high amount of energy, more than the red and yellow. So mercury contains blue color, and that's why the electron move to different level, but not in sodium because in the spectrum there is no blue color. Nearly all the large or dense objects emit thermal radiation, such as stars, planets, and even you as a human. An object's thermal radiation spectrum depends on only one property, which is the temperature. Which means you as a human, your body will emit light or thermal radiation, but you cannot see it with your eyes because your light is in the range of infrared wavelengths, which a range that you cannot see with your bare eyes. The thermal radiation spectrum is a continuous spectrum, so you can see something like that. This is a lion. You cannot see this picture unless you're wearing infrared glasses. In military fields such as army, they use the infrared glasses to see the thermal radiation of any living things behind walls. For example, I believe you played before in video games. You have wall like that. Normally, you cannot see what behind that wall with your eyes. But when you wear the infrared glasses, you can see human behind that doors. You can see him like this. You can see him as this picture of lion. Hotter objects such as fire and sun emit more light at all frequencies, and also they emit photons with higher energy. The whiter color, such as in the eyes of the lion, is the hottest area, while going to the black area is the coldest area. According to thermal radiation and different spectrum, we have black bodies and we have gray bodies. Materials with different colors, black, gray, white, whatever, will interact with the light in different ways. In physics, we have black and gray color. The absorption, reflection, emission of light different from black and gray and other different colors. So let's say we have a black body, any black body, such as charcoal, for example, and we have gray body, such as silver, for example. We have silver and we have charcoal here. When you hit that black body with the light, the black body will absorb the whole light and it will reflect nothing. So absorb 100% of the light without any reflection. So it's an ideal physical body finishing the whole job, meaning can absorb all the incident electromagnetic wave. This absorption occurs regarding the frequency and the angle of incidence of radiation. The black will absorb the whole light. In contrast to white body, the white body will absorb nothing but will reflect the whole light. Since the black body is a good absorber, it means it contains a lot of energy, making it a perfect emitter too, which means it will emit energy also. So the black body is a good absorber and a good emitter. The black body absorbs the whole light in different frequency. That means it can emit the light in different frequency to a different temperature either. What about the gray color? Well, it's imperfect black body, which means it's non-ideal physical body. Why? Gray body, something between the white color or the white body and the black body. So the black absorbs the whole weight, but silver will absorb part of that light, let's say 70% or 50%, for example, depends on the type of that gray body, and reflect the other amount of the light. So it absorbs part of the light and at the same time reflect the other part of the light. It can emit radiation as the black body. Whatever that gray body absorbed here, it can emit it later. It can emit all of that absorbed light or just some of it. So the gray color, something in between. It cannot absorb the whole light such as the black, and it cannot reflect the whole light such as the white. So it's non-ideal physical body. Something similar between them, both are opaque. The gray body and the black body both are opaque. We also have something we call it the spectral transmission. We have the transmission, which refers to the amount of incident light that successfully passes through any material. And mostly we calculate it or express it as percentage of light that made it through the material. So we have the glass, for example, and that's the incident light. The amount of light that passed through this material, we calculate it or express it by percentage. For example, 70% of light transmitted through this glass. That's the transmission. On the other hand, we have something we call it the transmittance. What's the difference between it and the transmission? There are two basic types of transmission. We have external and internal. Again, that's our glass and that's our incident light. Let's say the intensity of this incident light about 90%. And 80% pass through this glass because the other 10%, for example, reflected that 10%. Here the glass absorbed amount of the incident light. The amount of the transmitted light or the light that successfully passed through this glass, let's say about 70%. Because the other 10% absorbed by the glass. So starting from the intensity of the incident light as it enters the glass, versus the light's intensity after exiting the glass. That is the external transmission. So from the first one, before it enters and after it passes or exits the glass, that's external transmission. So an external started at 90 and exit as 70% intensity of the light. In internal transmission, we will determine or calculate the light intensity once it has entered the glass already. So we'll start calculating from this point, external from this point, while internal after it enters the glass versus its intensity after it leaves the glasses. From this area to this area, that's the internal. From 90% to this area, that's the external. The internal transmission primarily measures the light filtration ability of the glass itself, allowing you to get a more accurate idea of the glass's properties. And this one is very important when we use, for example, optical glasses or when we produce the sunglasses. Okay, again, what about the transmittance? Transmittance refers to the amount of light energy that the glass absorbs, such as this area, scatters, or even reflects. This calculation allows you to determine the ratio of transmitted radiant power to incident radiant power, giving a greater idea of a glass's ability to block photons. So transmission, this one, succeed to leave the glass. During that, the glass will absorb amount of the light energy or reflect some of that light energy, and that's immediately the transmittance. So this transmittance will depend on the absorption and reflection properties of the glass, and also very strongly depends on the wavelength of the light. Since the transmission we express it by percentage, so its value from 1 to 100%, but the transmittance from 1 to 0. We can say this glass, for example, has transmittance of 0.9. How can we take advantage of spectral transmission? Well, different wavelengths transmitted in different value. That's our glass. For example, this will transmit easier. And we can use a coat here or a cover here to prevent this light from entering the glass. We quite use this idea in the sunglasses, for example, or glasses with filters to allow some colors to pass while preventing the other colors. Mostly we use it to prevent the UV, for example, and the infrared to pass to your eyes. Or we can use it to tint car windows. And how can we calculate the transmittance? We have the incident light and we have the transmitted light. We will calculate the power of the transmitted light to the power of the incident light.